So thank you for the introduction. It's great to be able to, well, I wanted to say it's great to be in Vienna, but unfortunately, last week, my daughter brought home Omicron from kindergarten. And so I'm still sitting here in Bayreuth and wasn't able to travel. But fortunately, we're living in time of the internet. And so I can give a talk online, and that's great too. Spiral Galaxies. These are beautiful objects, and we are living ourselves right in the thick of one. And these galaxies still ask us many riddle. And in my talk, I can give to some of them new answers. And the key are dynamical models for these galaxies, which are self-consistent. So they are a stationary solution of a suitable Vlasov-Poisson system. And these models have many properties which conform to observations very well. So these models really resemble a galaxy like we can find it out there. And we can learn quite something from these models. For example, I mentioned it here in the subtitle. We can learn something about dark matter. I will restrict myself to the spiral galaxy in which we are living ourselves, to the Milky Way. And here for the introduction, I show you a panoramic image of our galaxy like we can observe it in the sky. This panoramic image spans the entire space around the entire sky around the sun, and was taken at the European Southern Observatory. In the center of this picture, you see the central bulge of our galaxy. This is a dense huddle of many stars. And to the left and to the right of the central bulge stretches the disk of our galaxy, which appears here in this image as a horizontal line due to our position inside of the disk. And most mass that we can observe in our galaxy is concentrated in this disk. It is made up mostly of stars and of gas, whereby stars dominate the central parts of the disk and the gas dominates the outer parts. Next, I want to show you a cross-section through the model, which I plan to construct with you and to study in more detail. In the center of this model, marked with red dots, you see the bulge of the galaxy, which is an extension of about 2 kiloparsec. To the left and to the right stretches the disk. First, the stellar disk, which is marked by orange dots, orange crosses. These two parts, the bulge and the stellar disk, will be rigid in our model. So I include them as so they are not dynamical. And then we have the third part component of our galaxy model. We have the interstellar medium. This component I model dynamically. It stretches out to about 20 kiloparsec, 21, and it has a central hole of with a radius of about 4 kiloparsec. And this component is interesting to model because dark matter is said to be necessary to explain the dynamics in the outer parts of spiral galaxies. And well, these are the regions where the gas of the galaxy, the interstellar medium, dominates the mass. How do the dynamics of this interstellar medium look like? The mass in the interstellar medium is on almost circular orbits around the center of our galaxy. And this almost is important. One could be tempted to say, let's simplify everything and place the mass on perfectly circular orbits. Such a model would be easy to construct, and then we are done. But this would be a bad idea, because models in which all mass is moving on perfectly circular orbits is highly unstable. Such a model destroys itself very fast. So it's important that we have at each position in the disk a dispersion of velocities. And this is what makes things a bit difficult. The mass of this interstellar medium is made up mostly of gas, and the density is extremely low in this interstellar medium because it distributes over vast regions. And therefore we will model it at a collisionless gas, which moves in its own gravitational potential and the gravitational potential of the bulge and the stellar disk. And what I've said just makes it an ideal candidate to be modeled as a stationary solution of a suitable Vlasov-Poisson system. And this is exactly what we do. We model the ISM. This were the blue crosses in the previous slide, distributed between 4 kiloparsec and 21 kiloparsec. We model this ISM with an axisymmetric distribution function. So by assuming axial symmetry, we ignore at first the spiral structures which can be found in the Milky Way, but we will re-encounter them later. This distribution function f depends on velocity on position x and velocity v, and both position and velocity we only choose in R2. So we constrict the mass of the ISM, which is concentrated in a thin disk. We concentrate the mass into the plane. This and ignore motions in z direction. This simplifies things a lot. And it's justified since this disk is very thin. And we say that F shall be a stationary solution of the following Vlasov-Poisson system. In the first line, we have the Vlasov equation, where the gravitational potential is the gravitational potential of the whole galaxy, so of the ISM, of the bulge, and of the stellar disk. In the second line, we have the flat density, which corresponds to F. We get it by integrating simply over the velocities. The third line is interesting. There we have the gradient of the gravitational potential of F, so the gradient of the gravitational potential of the ISM. This is given by G, the gravitational constant, times the convolution of x divided by length of x to the third, and the density sigma. And this convolution is in fact a singular integral operator, because the singularity of the integral kernel is not integrable over R2. And this makes this convolution sensitive not only to the function values of the density sigma, but also to the derivative of sigma. For example, since the ISM has a very sharp, a relatively sharp border, so it's decaying rapidly at its outer border at about 20 kiloparsec. This causes in this region larger forces than one would expect by just looking how much mass is there, because this rapid decay generates strong forces in the neighborhood of this rapid decay. And then we have the last line where we close the system of equations. The gravitational potential of the galaxy is made up of the gravitational potential of F, which models the ISM, plus the one of the stellar disk, plus the one of the bulge. We want that this is a model for the Milky Way. So the first question we should ask is, where do we get the gravitational potential of the galaxy from, gradient U-gal? Since the potential of the galaxy and the potential of the model should match. This we get from the dynamics. As I've said previously, the mass is on almost circular orbits around the center. and where we have a dispersion at each position. So we have, when we look at some radius, we see different velocities. But from the dispersion profile, we can deduct which velocity must correspond to the velocity on a circular orbit. And this was done, for example, in 2019 by Eilers et al. With high precision for the Milky Way. And here you see the circular velocity curve of the Milky Way. So at each radius, we see a dot which marks the velocity that corresponds to the velocity of a circular orbit at the given radius. And the velocity on a circular orbit is related to the gradient of the gravitational potential of the galaxy via the following simple formula, which you see on the bottom of the slide. The circular velocity squared at radius r is given by the radius times the derivative with respect to r of the gravitational potential of the galaxy. Here I've written the gravitational potential as a function of r since we assumed axisymmetry. And if you remember this cross section that I've shown you at the beginning, the interstellar medium can be found in a region between 4 kiloparsec and 20 kiloparsec. And when you now look at this diagram of the circular velocity curve, we see that in the region between 4 kiloparsec and 21 kiloparsec, the circular velocity curve is almost flat. It's slightly decaying, yes, but it's almost perfectly flat in this region. So it's worth to study first a toy model where we assume a perfectly flat circular velocity curve everywhere. So the circular velocity is constant from radius r0 to radius infinity. Such a model, such a disk which allows such a flat circular velocity curve everywhere is called a Mestel disk. And the potential of the Mestel disk can be written down quite simple, because if you use this formula on the previous slide about the circular velocity curve, you see directly that the potential of such a disk must be given by circular velocity squared times the logarithm of r, because if you take the derivative, you have circular velocity squared divided by r, and then you substitute in this simple formula, and you see that's exactly the potential that we need. The density of such a Mestel disk is a bit more difficult to find, but once you found it, it's easy to write down. We just need a constant Cm, which depends on the velocity, divided by r. And then we see that the third component of the angular momentum, z, which is given by x1 times u2 minus x2 times u1, is conserved along orbits in this potential of the Mestel disk, since the potential is axisymmetric. And the local particle energy, E, which is given by the potential plus the velocity squared divided by 2, is also constant because the potential is time independent. And then we want to equip this toy model, this disk, with self-consistent dynamics, and therefore we do the standard trick. We just search for a function, distribution function Fm, which depends only on the angular momentum and the energy, because then the distribution function is constant along orbits, and therefore it's a solution of the Vlasov equation. And for self-consistency, we need that the density which belongs to Fm is exactly the density of the Mestel disk. And we want that this distribution function Fm has similar dynamics like the real galaxy. So we want that most mass is on almost circular orbits around the center of the model. And therefore, it's good to take first a look on angular momentum and energy on circular orbits. The angular momentum LC on a circular orbit is growing linearly with radius, since the circular velocity is constant. And the energy on a circular orbit is growing like a logarithm, logarithmically with radius, because the potential of the Mestel disk is a logarithmic one. And if we then draw this curve into a diagram, we get a logarithmically shaped curve. And this is what I sketched here. I've sketched here the half plane where LZ is greater 0, because this way we have only rotation in one direction around the center. This curve of angular momentum and energy on circular orbits divides the right half plane into two halves. In the area below this curve, below the curve LC-EC, we won't find any orbit. Every orbit in the potential of the Meskel disk has an LZE pair, which is located above this curve of angular momentum and energy on circular orbits. And we want orbits which are almost circular. These are these orbits which are close to this curve LC-EC. And then we choose a stripe of constant thickness along this curve of angular momentum and energy on circular orbits. This is this orange stripe here. And we want to define Fm, the distribution function, only on this orange stripe, because this way we are sure that there's only motion which is almost circular. And if you search for distribution functions, you can find quite a lot of them. And I've written down the simplest one. We can define the distribution function Fm on the orange stripe by a constant, Cn prime, divided by the angular momentum Lz, and we set it to 0 elsewhere. If we do so, we get a stationary solution of the flat Vlasov-Poisson system for the Meskel disk. And we see that the dispersion of velocity is independent of radius. So we have a constant dispersion of velocities at each radius. And when we look which thickness of the stripe do we need to produce a certain velocity dispersion of velocities, we see that the thickness of the stripe must be 2 times sigma squared. I sketched it on the top and in this orange stripe. I've written down it there. And if we choose the thickness of the stripe such 2 sigma squared, we get always a dispersion of velocities sigma. And this, if we choose realistic parameters for sigma, the velocity dispersion, we get a very, very thin stripe. So the stripe is much thinner than sketched here. If I would have drawn a diagram which is true to scale, you would not have been able to distinguish this orange stripe from the black curve of circular of angular momentum energy on circular orbits. As long as we are here in this toy model, this does not disturb because, well, we have a smooth concave curve, and above this, well, then we just define simply a very narrow stripe, and then we have our dynamics. But when we go back to the Milky Way, the potential of the real galaxy will cause several bumps and wiggles in this curve of the angular momentum and energy on circular orbits. And these bumps and wiggles will be much larger than the thickness of this orange stripe. But as long as we choose this orange stripe along the curve LC-EC and follow all the bumps and wiggles of the which are caused by the potential, we will be able to construct self-consistent dynamics for the interstellar medium 2. And the idea is simply to cut out a central section of this orange stripe, which represents the dynamics between 4 kiloparsec and 21 kiloparsec. And when we do so, the density, which corresponds to this cut-out model, looks quite similar to the density of the real interstellar medium. So we get by choosing a cut-out section of this dynamical Mestel disk as a model for the ISM. By doing so, we get both. We get dynamics, which are similar to the dynamics of the Milky Way's ISM, and we get a density that is also similar to the density of the Milky Way's ISM. Then we have to think about how much mass do we equip with this dynamics, and we have to re-include the bulge and the stellar disk, which we have ignored up to now. And we also have to think how much mass do these two components need to have. And the only thing that we lose by doing so is that we lose the self-consistency of the dynamics. And this self-consistency we want to restore with the following algorithm. This algorithm that I will should explain is an improved version of the algorithm that was first used by Håkan Andreasson and Gerhard Rhein in 2015, where they also tried to construct self-consistent galaxy models. And the major improvement is that here with this algorithm, we really get dynamics which are almost circular around the center of the, which describes almost circular motion around the center of the galaxy. So the mass is moving exactly like in the real galaxy. And this was not the case in the models of Andreasson and Rhein, because their most mass was on radial orbits which pendled through the origin. So how does the algorithm look like? We start with a potential U0, the potential of the Mestel disk. And we assume that we have given some potential UE. Then we calculate for this potential the curve of angular momentum and energy on circular orbits. We define then a stripe of constant thickness 2 times sigma squared above this curve. This was this orange stripe that you had just seen before. And on this stripe, we define our distribution function Fe, exactly like the one for the Mestel disk. We define as a constant divided by Lz. And this we multiply by a suitable cutoff function K, which cuts out a central section of the orange stripe. And we set the distribution function to 0 elsewhere. This constant now is no more the constant that we used for the Mestel disk. There we were constrained to use a certain constant to get self-consistency. But this C will now be a free parameter. And in the next step, we choose weights for the 3 galaxy components, ISM, bulge, and stellar disk. So we prescribe the densities of the bulge and the stellar disk, and then we choose the prefactor such that the circular velocity curve of the model matches the circular velocity curve of the real galaxy. And then we define a new potential UE plus 1 by summing up the potential of Fe plus the potential of the stellar disk plus the potential of the bulge. It's justified to ask a question is if this algorithm is likely to converge, because in particular we modify our ansatz in each step. But when you look at this algorithm, it's quite obvious that it has a good chance to converge at least. because in the fourth step, we take care that the circular velocity curve of the model and the one of the Milky Way look similar. So the potential of our model does always look similar to the potential of the real galaxy. And so the potential does not vary, does not change much between each step of this algorithm. And since the potential is responsible for the shape of the curve of angular momentum and energy in circular orbits, this curve does not change much. Hence, the orange stripe looks quite similar between each step. And also Fe is similar in each step. And well, this algorithm does indeed converge very fast. If we stop it after about 10 steps, we cannot distinguish anymore the distribution function that we get from a self-consistent, from a stationary solution. So this algorithm gives us a stationary solution. And the first question that we should ask is, here in the algorithm, we tried in each step to reproduce the circular velocity curve of the Milky Way. And the first question should be, did we manage to reproduce this curve? And the answer is yes. This algorithm produces a circular velocity curve that resembles the one of the Milky Way quite good. Here with thick dots is marked again the circular velocity curve of the Milky Way as measured by Eilers et al. In 2019. The solid curve is the circular velocity curve of our model. And this curve fits the observed curve quite good, I would say. It's a quite good fit. And then with blue color, I have marked in this diagram the dispersion of velocities of the model. So the blue color marks the velocities with which, when you remember the cross-section from the beginning, this blue color marks the velocity with which the mass comes out of the cross-section and flies around the center of the galaxy. And the thickness of this blue stripe can be chosen arbitrarily, because we can enter the dispersion sigma as a free parameter, choose the dispersion sigma as a free parameter in the algorithm. And the sigma says how thick do we have to choose the stripe on which we define our ansatz function. And well, yes, so we can choose it freely. And the next question that we should ask ourselves is that how much mass do we need to create this circular velocity curve? The circular velocity curve needs a gravitational potential which enables this almost circular motions. This gravitational potential must be created by some mass. And physicians use normally dark matter to explain this circular velocity curve, to explain the gravitational potential. And since we did not include dark matter in our model, we must have a mass gap, because well, somewhere must the mass be that creates this circular velocity curve. How large is this mass gap? I compared my model, the masses of my of my model, with a model that is given in the textbook of Binney and Tremaine from 2008. And there we see that the total mass of the model here is about 3 times the mass of the bionic components in the model of Binney and Tremaine. And this is exactly what one should expect when we try to create such a bionic model. Because within a ball of about 20 kiloparsec. In the model of Benny Tremaine, they have about 1/3 of the mass is bionic within this ball of radius 20 kiloparsec, and 2/3 are made up by dark matter. So we'll need about the same mass as they to create a circular velocity curve. And so we will need about 3 times the mass of this bionic component. The nice thing is then that this mass distributes almost uniformly over all 3 components of our model. The bulge has to be about 4 times as high as the one in Benny Tremaine. The stellar disk has to be about 3 times as high as in Benny Tremaine, and the ISM has to be about 4 times as massive. And so these are we won't be able to find smaller factors for this mass gap, but well, this model finds at least the smallest one which are possible. It's difficult for me to discuss these factors in detail because I'm not a physician. I can't interpret all this observational data on myself. But at least these factors are not gigantic. So for example, if you look on estimates how much mass, if you look on estimates how much stars can be found in the Milky Way, then reasonable estimates range from 100 billion stars to 400 billion stars. So these uncertainties are not uncommon in astrophysics, but okay. But I want to share at least one small notice that made me smile when I found it, to try to convince you that it could be possible to explain these factors. The 2 Voyager probes, which were launched in the 70s, have just recently reached the interstellar medium. We are here in the solar system, are living in a void, which is created by the sun. And then there's a hard border beyond which the interstellar medium begins. And the 2 Voyager probes have crossed this border 4 and 10 years ago. And since these 2 space probes are out there, they constantly measure a density of the interstellar medium, which is about 3.5 times higher than was calculated a priori. And this would be exactly a factor of the magnitude we would need here. But well, as said, it's difficult to discuss these factors further, but I can do at least one more thing. I can do a second thing to check if these models are realistic or not. These models are a self-consistent solution of a suitable Vlasov-Poisson system, of the flat Vlasov-Poisson system, which I have shown you before. And we can ask, are these stable solutions? Are these solutions stable? And the answer is no, they are unstable. They can suffer from 2 instabilities. And this is good, because these instabilities make my model behave realistic. I want to show you the first one. You have chosen, on the right, you see a simulation, snapshots of a simulation, where the dispersion of velocities was taken to be 11 kilometers per second. This is quite a reasonable value. And to understand what happens in this simulation, you have to look on the accelerations which are active in the direction which is tangential to circular motions. So when you move on a circular orbit, you look on the acceleration that you have tangential to the movement. These accelerations are 0 in the axially symmetric model, because due to the symmetry. Here in the simulation, these tangential accelerations are very low initially, but they are different from 0 because I've drawn the particles at random from the distribution function. And when we now run the simulation, these tangential accelerations will grow exponentially. And these growing tangential accelerations correspond to local overdensities, which become denser and denser, and which result in a beautiful four-armed spiral structure, which is quite similar to the one that you see here on the left side, the one of the Milky Way. This picture is an artist's impression of the Milky Way, which is based on observational data from NASA and from ESO, and it's published on their website. And both pictures share the same scale. And when you compare them, well, they look astonishingly similar. Obviously not in the center, because this I've not modeled. But well, the ISM cannot be found in the center. When we continue the simulation, we see that the spiral activity is strong for about 1 gigayear. Afterwards, it becomes weaker, and the model, the particles, the simulation, converge to a new, again, axially symmetric state. Yes, and for a comparison, the age of the universe is about 13.8 gigayears, and the Milky Way is thought to be about nearly as old as the universe. No, this I wanted to say later. I've forgotten what I wanted to explain first. Why does this spiral activity vanish from the model? What happens there? In this 1 gigayear, where the spiral activity is strong, the arms move with the mass. They permanently disrupt and merge with each other and form anew. And while the spiral activity lasts, the mass passes permanently through the arms. It enters the arms and goes out of on the other side. And while it passes through the arms, it got deviated, and hence the total deviation, the dispersion of the model rises. Initially, the dispersion was on a low realistic value of 11 kilometers per second. And during this gigayear of spiral activity, the dispersion has risen to about a value which is about 4 times as high as the initial one. This higher dispersion stabilizes the disk, and the spiral activity vanishes. And now, for comparison, the age of the universe is about 13.8 gigayears, and the Milky Way is nearly as old as the universe itself. So this seems not to happen in the Milky Way, because the dispersion in the Milky Way is everywhere low at a value somewhere around 10 kilometers per second. And the spiral activity seems to last forever. This is the same also in other spiral galaxies. So there must be something that is different in the Milky Way and my model. And in the astrophysical literature, it's explained as follows why this does not happen in the astrophysical literature. It is explained as follows why the dispersion does not rise. The mass of the interstellar medium is not a homogeneously distributed gas. The mass is concentrated in large clouds, and 2 of such clouds I have sketched here in this on the right. As long as these clouds move on almost circular orbits around the galactic center, everything is fine. But after these clouds pass, for example, to a spiral arm, they get deviated, and the orbits of such clouds will intersect, and the clouds will collide with each other and continue on with a velocity which corresponds again to a velocity that is on a circular orbit. So this collisions reduce again the dispersion once it has risen due to the passages through the spiral arms. This I have not modeled here in this model, so I have not included such collisions. So it's not surprising that the spiral activity vanishes. And this dissipative process is said to be responsible that the dispersion in the Milky Way is everywhere at a low value of about 10 kilometers per second. And this is quite a typical value for spiral galaxies. I show you here a histogram of the velocity dispersion in 20 nearby spiral galaxies. This is a sample that was studied by Leroy et al. In 2008. And you see that most spiral galaxies have a dispersion somewhere around 10 kilometers per second. And then I've drawn here also an estimate for the dispersion of velocities in the Milky Way. This was calculated by Marosco et al. In 2017. So the Milky Way falls into this class 2. But then one question arises. This dissipative process, which I have described on the previous slide, seems to be strong because it keeps the dispersion of the Milky Way everywhere on this low value, about 10 kilometers per second, and the dispersion does not rise due to the spiral activity. So this process is strong, but if it's strong, why does it not reduce the dispersion to 0? I searched for an answer on this. In the astrophysical literature, I have not found one yet. Either they describe this process or they measure the dispersion and say, well, it is like it is. But when we look at this histogram above, we see that there's a large gap between 0 and the observed dispersions in spiral galaxies. So why is it not possible for this dissipative process to reduce this dispersion further? My model has an answer for this question. And therefore, I want to show you the second instability that can be present in these models in action. Here I show you 3 simulations where I have enforced axial symmetry. This I have done to suppress the formation of spiral arms. In the left, all 3 simulations has a very similar mass model that lies that corresponds to the simulation, but the dispersion is different in each simulation. In the left simulation, you have a dispersion of 0 kilometers per second, so everything is on purely circular orbits. You don't have a dispersion. In the middle slide, in the middle simulation, we have a dispersion of 9 kilometers per second. And in the right model, we have a dispersion of 11 kilometers per second. And when we run now these simulations, we see that after 400 gigayears, the left model got destroyed. After about 400 megayears more, also the middle one got destroyed, but the right model stays stable as long as we continue the simulation. The responsible instability, which destroys the 2 leftmost models, is called the Jeans instability, and it triggers when the dispersion of velocities is too low. And we can stabilize a disk against this instability by increasing the dispersion. And this is what's happened in the right model. And this Jeans instability does not only rearrange the masses, it also increases the dispersion again. And any dissipative process, however strong it might be, will not be able to reduce the dispersion below the threshold between the Jeans instability and stability, because once the dispersion is reduced below this critical value, the Jeans instability starts to work against it and increases the dispersion again. And when you look at this threshold, on the value of this threshold, then this value coincides almost perfectly with the observed dispersion of velocities in the Milky Way, in spiral galaxies in general. So this is an explanation why the dispersion cannot be reduced any further. And I'm looking curious forward because I plan to tackle this problem next. I'm curious looking forward to how this dissipative process will fight against the Jeans instability, if this really gives realistic results. But that I have not done yet. But I think this is a strong argument that suggests that the model that I have constructed might indeed be a good image of the real galaxy. And now one last question. What about dark matter? I've ignored it completely in this talk. Well, when I started to treat this problem, I left dark matter away because, well, it's invisible, and I just didn't know how to model it. Because there are so many free parameters that you can include in a model that I've said, so which parameters should I choose? And then I constructed an algorithm that gives me this ionic models, and I've seen that these models are quite powerful. Well, I did not continue with dark matter. But what about dark matter? Dark matter is in general said to be necessary to explain the circular velocity curve of a spiral galaxy. As we have seen in this talk, this can also be achieved by a bionic model, and the mass gap is not gigantic, I would say. It seems possible that one could explain this mass gap. But then the second question is, can a model that uses dark matter explain the two dynamical phenomena that we have just discussed, the spiral activity and the dispersion of velocities in the ISM? Can a model that uses dark matter explain these two phenomena equally well? And the answer is no, well, at least not ad hoc, because dark matter provides too much stability. When you study a lower mass disk for the ISM, which is embedded in dark matter, this dark matter stabilizes this lower mass disk against both instabilities, against the instability which causes the spirals, and it stabilizes the disk against the instability, against the Jeans instability. So we could, in a model that uses dark matter, we can place all mass on perfectly circular orbits, and everything would be stable. So a model that uses dark matter needs some other explanation for these two phenomena. And so I think these bionic models with their self-consistent dynamics, which I have shown you today, will prove quite a good challenge for the dark matter hypothesis. Okay, well, if there are any questions, feel free to ask. Otherwise, thank you for the attention. And that's it.